So the first time we watch the video, it'll go normal speed, and you'll just see what's happening. Then it will go through it again in slow-mo, and then it will show us what the answer should have looked like, okay? So we're going to start with measuring the guy's waist off the ground. I'm thankful that other people made these videos so I didn't have to, like, go to the playground and do this myself. They don't really have sound, so. So watch his waist and you can just sketch. Okay, so what it's going to do now is it's going to go back through it at half speed, okay? So that you can get a better idea of what it looked like. Okay, so go ahead and take a minute and sketch what you think it is, and then share with the people around you what you think this graph looks like, and then we'll look at the answer and see how close we were. Okay. All right, so they say the graph looks something like this, okay? We probably had some variations on this. I walked around, I saw what you guys had, but most people had similar things. Maybe the part where he sat down, we didn't account for the drop in his waist right away, but same type of idea. And notice that most of this is made up of a linear function, right? And it's all connected, kind of like what we saw when we had somebody walk in front of the calculator-based ranger and measure their distance over time. And almost every part is linear. This part at the end, we can start seeing some other functions. And later in our course, as we learn other functions, we'll be able to incorporate them into our piecewise graphs, okay? All right, so we're going to look at a different one. Let me find the one that I want here. I have a specific one that we do. Hopefully they didn't take it off. Okay, so we're going to look at two of them. Oh, did they take off the ponies? Let me see. Let me pause this. And so you're going to see him set the cups on the scale.
1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15.
All right, and now they're going to do it in half speed. So again, you're just making a rough sketch. You don't have to be perfect. They're talking during half speed's extra entertaining. All right, so take a second and sketch what you think is happening, and then we'll check out their solution.
1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15.
Okay, so I would argue that they didn't just do the weight of the stack. They actually did the number changing on the scale, right? Which to me is slightly different than the weight of the stack, because like when you put the cup down, it weighed one thing, right? But the numbers on the scale had to like change to adjust to that amount. So to me, they were graphing like when you get on the scale, you don't write down all the numbers in between while it counts up to your actual weight, right? You wait till it gets to your weight and then you're like, that is my weight. It just took a second for the scale to get here. So what they did was they graphed all the numbers that you were seeing flashing on the scale, right? So this one increased incrementally this way, then like this, then like that, and then like that. So you see when the different weights, you see the slope of the line changing a little bit, right? But because they just counted constantly the number changing, that was it. How many of you guys had something more that counted like the weight of the cups? Like once 2 were on here, it's flat this way for a while, and then it jumped up to the next one, something like that. Okay, so I don't think you're wrong. I think it's that they had to be specific about what they were counting when they were counting weight, right? They were counting like the flashing numbers on the scale, not like once I put on the second, it counted like this. So the one we do next will be a little more clear in what they're counting. So they are counting in this one the size of their hand. I think they mean like the number of cards that they're getting handed out, okay? Not like the actual size of their hand, okay? Because they have cards that they're going to pass out. So we'll go ahead and watch this and see what we think. So remember, it will do it full speed and then go through half speed. So yeah, size of hand is cards per person. So you're trying to count how many cards there are per person. All right, now here it goes at half speed. All right, so take a minute and sketch what you think is happening. So they counted once everybody had that amount of cards. All right. So a couple of things about this graph. You could have counted slightly differently. How many people got something like this? You had horizontal marks. You counted 1, then 2. How many of you had them where they weren't connected, like this one, like a horizontal line, then it jumps and it's another horizontal line? Right? So our brain tends to, based on what we've seen, that they should all be connected, right? But it actually doesn't make sense to connect them with a vertical line. It then wouldn't be a function like we're looking at, right? And if we connected them with a line that had some sort of slope, that meant there was like some incremental change, but we're counting like whole number of cards. So it completely just stops at one point as being 0 or 1 and jumps to the next. Now, if you had this counted 1 like right when they started, because you counted like 1 as like until the first person got to 2, that would be fine. They would have to clarify exactly when we're counting that each person has 1 card or not. They waited till every person had that amount of cards. So this graph is a special kind of wise function. For this first situation here, the equation for this graph, 1, right? 2, because this was 1, 2, 3, 4, 5, okay, would be expression or equation that's equal to like each piece. What kind of format would it be in? So it'd be f of x equals, you'd have this big bracket and you'd have these like 5 pieces listed. What would those equations look like? Would they be quadratics? Would they be, what's that? Yeah, they would just be whole numbers, right? The whole numbers that you see here to graph that constant type of function. So there are actually some different rounding functions in math that do this. There are some different brackets that mean to round things a certain way, and they just round always to a whole number. Some of them round how you think of rounding, like where 0.5 is like the up versus down part of it, and others of them always round down or always round up. Like it doesn't matter if it's 9.9, it will always become 10, or it will always become 9, depending on the type of function that you define. So today the function we're going to study is a function that behaves like this. It doesn't have just 5 pieces. It continues that pattern forever and ever and ever. So you couldn't really write it as a piecewise function because you have to have like, I don't know, a dot, 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 and people would have to understand the pattern or something in it. So doesn't really make sense of how we'd write something. So we use one of these notations for how to round stuff to write an equation in just one equation without multiple pieces to describe all these horizontal lines that we're going to get. Okay? So the function we're going to study today looks like that. The way we get something like that is a life situation where we only count whole number of things, or a mathematical operation that rounds things to the whole number and doesn't account for anything in between there. All right? So we're going to take a look at our note guide and go through some examples. So the first thing we're going to do is just understand the notation and what it's called and how we use it, okay? So the function that we're going to study is called the greatest integer function. The name can be a little deceiving. So I wrote the definition out here and we're going to kind of process through it. So the greatest integer function is a function that rounds the input value, so whatever's inside these brackets, okay? It rounds it to the nearest integer that is not larger than the thing that you have inside the brackets, okay? So right here you have 2.7. It's inside of those brackets, okay? So if we're going to round 2.7 to integers near it, what are kind of your two options? What are the two integers that surround 2.7? 3 and 2. So it's either 3 or 2, okay? So now the question is which one? And so we have to go back to the definition. Which one is not larger than the number that's actually in the brackets? So when you're looking at this, and you're either going to round it to 3 or to 2, which of those numbers is not larger than 2.7? 2. So this actually gets rounded to 2, okay? So that's what we're going to do, is round it to 2. Sorry, my computer is a little bit, I don't know. Now we're doing lots of other things. They're just happening. Okay. Oh, no, apparently I'm pushing the wrong button. Sorry, you guys. Clearly been a while since I used this software. Like this, maybe. There we go. Okay, so this gets rounded to 2. What about here? We have a 4. 4. So it doesn't really require rounding. And we don't round it down because 4 is still not larger than 4. So it can remain that value. Okay. What about 0.3? 0. What about negative 3? Good. And what about negative 5.4? Negative 6. Yeah, negatives are kind of tricky, right? We don't want to say 6 because to us 6 is bigger than 5, but really negative 6, okay, is still smaller than negative 5.4. So are we okay with the notation and what it means? That these brackets don't mean absolute value. They don't mean they're just parentheses. They're actually an indicator of this new function that you're learning, and it operates in this specific way. Are we good with that idea? Okay. All right, so now we're going to look at the parent function graph and then what happens when we change some things about the graph. So for the parent function graph, remember all the parent function means when we use that word is that we're taking the simplest form. No a, no h, no k value. Okay, no numbers being added, subtracted, or multiplied in, just the simplest form of that function. Okay, so let's think what happens if we made like a table for this graph. So if we make the table, I'm going to plug stuff in between these values in a minute. We want to look for a pattern because we're really unfamiliar with this. We're not going to graph it by using a table every time. It's not that tables are bad, but you know how like once you learn quadratics are shaped like U's or whatever? What if you use a table and you're only getting this part of the U the whole time, like one side of it that's going up? You need that like turnaround point to see the shape of the graph. So we don't generally use tables all the time to get our graphs. We use them as a tool but pay really close attention to what to center them around. But when we're first learning how something behaves, we kind of use it as something to explore. Okay? So you guys saw what happens when we plug in the integer values, we just get their own integer value back. Like they didn't have to be rounded, right? So all of these will just give us the same value we would normally get if whether or not those brackets were there. And so those points on our graph, -2, -2, -1, -1, 0, 0, 1, 1, 2, 2, okay? And this would continue infinitely. So like this pattern of points would keep going. So it feels a lot like a line right now, but I should know with those brackets and what we viewed before and what we're talking about doesn't behave like that. So let's look at the stuff in between, the stuff that does get rounded and what it gets rounded to. So let's say in between here you did like -1.5. What does that get rounded to? -2 when we plug it into this function. Okay. What if you had picked -1.1? What does that get rounded to? Still -2. Yeah, like, right, a little trickier than what we're used to. What if it was -1.9? -2. Basically, when we were equal to -2, we're going to be equal to that all the way until we reach -1, and that's the only time it jumps back up to -1. So these x values between -1 and -2, they all get rounded to -2. So I plug in -1.5, I get -2. I plug in anything there, I keep getting all these points along here equal to -2 until if I went past -2, they'd get rounded down to -3, right? Down here. If I go past -2 the other way, they would finally reach -1 and go that way. So what these look like are these horizontal line segments like we said we'd see, and then they have this open endpoint at the point that they jump. Because remember, we said all the way up until it reaches -1, then it'll get rounded to -1 instead of -2. But when is the number right before -1? We've had this discussion before, right? There is no number right before -1 because there's numbers. So that point just tells us, you know, everything up until that, then it goes here. But you would have seen the same thing here at -3 before it jumped to -2. Okay, so this graph follows this pattern that we see here. It specifically stays the same and gets rounded there, but it's open here because that one gets rounded to a new point and everything stayed the same right here until we finally got to that new x value. Okay, so this is what the parent function looks like. Is this okay with everybody? Like, you now have in your head these brackets mean this greatest integer thing and how it rounds, and you now know that its graph would look like this. Okay? So some notes about the graph, because when we start building new graphs, we don't want to plug in points all the time. It could get really tricky because you might not exactly know what points to plug in. What if they stretch out the steps or they push them down? Like you saw with the absolute value v, right? It got wider, narrower, shifted over. This one's really complicated. We want to understand those things. If we start just plugging in random points, we might not get all the end points and stuff that we need. So we want to understand how it works really well. So the parent function has, so I would first make a note. This is me. You can write down whatever's important to you. I would want to note that this graph comes in steps. Okay. And then what are the characteristics of the steps? How long are they horizontally? How long does it take till we get something that we can plug into the greatest integer function that finally rounds to the next number? 1 unit, right? Everything in between keeps getting rounded the same, and then all of a sudden you reach that next integer and it rounds. So the steps are like 1 unit horizontally. What about how far they are apart? When it finally rounds to a new number, how big of a jump does the step make? Just 1 unit, right? So they're also 1 unit apart vertically. And they kind of look like they have a positive slope going on, okay? Which obviously could change when we put some different negatives in there and stuff like that, all right? Okay, what about the domain of this function? What x values are you allowed to plug in? Is there anything that if you plug it in here, say, it's not calculatable, cannot be found? No, you can put any number in here, right? And we'll just round it to a certain place. So the domain is still all real numbers. And then how do we describe the range? Yeah, then. Yeah, so for the parent function, and it could change. What if they shifted everything up half a unit? That would be super annoying. They'd still be a unit apart, but instead of landing nicely on all the integers like 0, 1, 2, 3, all those lines would land on 0.5, 1.5, 2.5. So in this graph, it's all integers. So if you guys don't remember, a bold Z is the set name for integers. Make a note of that if you have to. Okay. Do you guys understand why you can't just write from negative infinity to infinity? It does keep going forever. Like this step will keep going up and this one will keep going down. But why can't we just say it goes from negative infinity to infinity? Yeah. Yeah, there's like infinitely numbers in between there that we're never actually hitting or sitting on, right? And we can't ignore that. So sometimes we might just have to make a list for that because we haven't really learned some of the other notation. So we'll talk more about how we're going to write the range every time and stuff like that. But our range is definitely going to be unique. Okay. If these get stretched apart more and they skip like every 2, they might only be on evens or odds. Okay. They could be on weird things like halves like we talked about. So the range is going to be a little more complicated here, even though it always keeps going to describe exactly which numbers you're hitting. Is everybody okay with the parent function? Take like 10 seconds in your group right now and make sure that everybody understands how this parent function works and if they have any like weird questions that are lingering. Like, do you know why it has a closed endpoint and an open endpoint? Do you know why it has these horizontal segments? Okay. So if we look at the next page of our note guide, or if you just go to the next page of your notes. The coefficients can act in really different ways. So what we're going to do is try and kind of figure that out, okay? So we're going to use the same approach we did before, but then we're going to learn it. So like this plugging in thing is not efficient. But it's good for our mind to see what's happening with the plugging in, to understand why this is going to affect the graph a certain way. But this might have the same or a different effect on the graph, depending on if you're multiplying it by -1 before you do the rounding, or if you're doing the rounding first and then multiplying it by -1. Okay? So let's look at kind of the XY table like we talked about before. And if we had some numbers in there, I'm going to do a little bit less of a range of numbers now that we already understand. We already have an expectation. The minute you come to graph something that has these brackets right here now, what kind of picture do you see in your head? Yeah, steps, right? I don't know how long they're going to be, how far apart, if they're going to put them in a weird place with some shifting, but there will be steps, okay, because it's still going to round something at some point in time. So we know the general shape, but we want like a starting point. And the main thing here would be you could draw the steps if someone gave you a starting point, right? Told you whether the steps went in a certain direction and how far they went and went to make the leap to the next step and how far apart to make it. So those are all the things that we're going to try and be processing. We know before that our steps started at 0, 0. Their slope went very much like a positive line, and we went over 1, ended it before we did 2. So it was like ones. It was very simple because it was the parent function. So we want to see how this negative is going to change any of that behavior. Otherwise, we would just start the same place and graph it again. So when we plug -1 in here, it doesn't really have to be rounded. It remains -1, but then it gets multiplied by the negative outside the brackets. So it becomes +1. Okay. When 0 gets multiplied by a negative, it doesn't change, so it just remains 0. And here, this would be +1, but then when multiplied by the negative, would get -1. So the first thing we see here is a slight change in like the direction. Instead of our line looking like, our steps looking like they're going up towards the right, like a positive sloping line, these ones are going to look like they're going down towards the right, like a negative sloping line. Okay? The question is that the only change? Or like, are the steps now not going this way? Do they go the other way? I don't know. Okay? We have to figure out what's happening here. So let's look at some stuff in between. So in between 0 and -1, let's say we plug in -0.5. And are you guys okay if I don't plug in like also -0.1 and -0.9? Do we now understand that every number between 0 and -1 is going to get rounded the same, and then this negative will get applied to it? So I don't have to plug in a bunch. I just need to figure out what's happening before I made the jump, right? Kind of thing. So when I plug in -0.5 to the brackets, what does -0.5 get rounded to? It gets rounded to -1, right? It's between 0 and -1. We have to choose the smaller thing because we can't get a big number. So it gets rounded to -1, but then -1 gets multiplied by a negative and becomes +1. Okay? So when I'm plugging in -0.5, +1. So that means every number here between where this solid point 1 was and where this one was, where it made the jump, is going to be along this horizontal segment right here. Are you guys okay with that? We could plug in another one if you wanted. -0.1 would get rounded to -1 times 1 would also make, or times the negative would make +1. So we're getting this horizontal step that we expected here, and then an open end point, because we know that there sits that certain number that rounds it differently, and we already found that end point where that happens, where it's an integer inside the brackets. Once you get one step, you guys, you actually have the whole pattern, because you now know starting points, right? Because we plotted a few. You know how long your step is. How long is my step? Just 1 unit still, right? And how far apart between steps when I jump? 1. And you now know that this endpoint, the open endpoint, is this direction. The steps continue that pattern. They can't like flip-flop back and forth. They have a consistent way that they round. So I now know with that one step that the rest of these steps we're going to make an assumption that they go on forever. So as long as you guys draw like 5 of the steps or something like that, I'm good if you don't like keep drawing 20 of them. Mm-hmm.
I'm confused because, wait, if you plug in 0.5, it go to -1?
Yeah. So what will no, it'll go -1 because, it'll go to 0. Because when you plug in 0.5, right, when you do the brackets to it and you round it with this greatest integer function, it gets rounded to 0. 0.5 would get rounded to 0 because she's talking positive 0.5, right? Okay, so positive 0.5 is between 0 and 1. You have to pick the one that's not larger than 0.5. So that would be 0. So this becomes 0. The negative then doesn't affect 0, and it's just 0. So at x of 0.5, I'm at 0 for y. Is that okay? So what we want to do is to not have to plug these in all the time. It's really confusing. What we want to do is know the shape well enough that we can just adjust it every time we see something happen on our graph. So what we're trying to do is kind of say, oh, I now know how this behaves. Every time somebody puts a negative out here in front of the brackets, it's going to do this to my picture. So think about the picture you had before. I'm going to draw it up here in green, what the parent function looked like. So the parent function had this same graph right here, this part, but then it went like this. So what I'm drawing up here in green was your parent function from the other page, right? When we put a negative in front of it, we got this new blue graph that's up there. What did that negative cause? What kind of transformation? How would you explain to somebody, if you know this graph, whenever you see a negative here, just do this to it and you'll have the new graph. So what did that negative cause? What happened for this to turn to this? What kind of transformation? Did it translate, like shifting? Did it get squished or spread out in any direction? Or did it get reflected? Reflected, okay? But reflected over what? Good. It got reflected over the x-axis. See my original step from my parent function right here? If I flip that over on the x-axis and look at its mirror image, there's my new graph right here. See this step right here? If I flip it over the x-axis, I get this step right here. Do you guys see that with everyone? And why this one stayed the same? It's on the x-axis, right? So when you flip it over the x-axis, it's still there. So we're going to make a note right here that whenever this negative is outside here, that it seems to have taken my graph and reflected it over the x-axis. Okay? And then I'm going to try and give you guys some idea why that would make sense. When we make this XY chart here, okay, think about how we made it for our parent function. The X kind of represented like before you round, and the Y was like after. Is everybody okay with that? Like the X was before we rounded the number, and then the Y was like after we did this thing to it with the brackets. Okay? So your X and your Y are like what I plugged in before, what came out after. Which one of those is this negative affecting if you follow order of operations and like the stuff you do when you plug something into this function? Is this negative being applied to the number before you round or the number that you got after you rounded? After. That means, is the negative affecting the X or is it really affecting the Y value from our parent function? The Y value. Think about if you took all the parent function points that used to look like this, and then all you did to their Y value was multiply them by a negative, you would get this new set of points. And think about how that works. Using numbers if it helps you. We had the point 1, 1 in our parent function, right? Positive 1, positive 1. If that negative is applied to just the Y value, my new point would be 1, negative 1. 1, negative 1. That's what I got on my graph. And by applying the negative only to the Y, I'm taking something that was above the x-axis, and it's now getting flipped below the x-axis, and anything that was below the x-axis, so it already had a negative number here, when you put it is going to turn it into a positive and flip it above the x-axis. Okay? So by putting a negative in that position, they were really explicit about what that was going to affect. It's really affecting the things we used to think of as our Y values from our parent function and just changing those and flip-flopping them over that x-axis. Okay? So what do you guys think is going to happen when all of a sudden they put the negative inside of the bracket? Good. It's going to reflect over Y because now that negative is multiplying who? Is it going, are you going to apply that negative to the stuff before you round it or the stuff you got after you were done rounding it? Before, because if you plug a number in right here, what's the first thing you're going to do to it? Apply this negative to it and then round it. So now what you're doing for your, if you compared it back to your parent function, is you'd be changing all the x's real quick, but you're not really doing anything to the y's. You're not doing anything extra after they were rounding, okay? So is it okay with you guys if we try, and I can go do the chart in a second too, if we try to just write the parent up here real quick and think about what it would look like if we just reflected it over the y-axis without plugging in all of the points, okay? So I'll do the parent function again in green. So what we got previously on the page, you guys have it to look at. I don't have it here, and sometimes I need to physically do it on the graph, especially when I'm just kind of getting this concept. So this was our parent function, right? I'll even write this here in case you guys look up and think that's part of the graph. So the green was our parent function. If we think of this negative as changing our chart that used to say x, y into a chart that now says change the sign of the x but keep the y's that went with it previously, okay? We talked about that if you're changing the x's that used to be positive are now going to be negative, but the y's not changing, and the x's that used to be negative are now going to be positive. So we said this is going to cause a reflection over the y-axis, okay? So this point right here, this origin 0, is that point going to change? If you're flipping stuff over the y-axis, is this point right here that's on the origin going to change? No, it's on the y-axis, right? So if you flip, it's still going to be right here, that guy. So that point's going to stay, okay? Before, the step behavior went a unit towards the right, and then that's where we made the jump. But what's going to happen to that visually if we're reflecting it over the y-axis? Yeah, all this points over here, like this positive 0.5, comma 0, is now going to be negative 0.5, comma 0. So we're going to see this kind of behavior. It flipped that way, okay? When this step here flips over there, this point is going to go here, and the whole step is going to flip over like the reflection in the mirror. So you're going to see something like this. Okay. Once you have one or two steps, you can ignore the parent function and you can just follow the new pattern that you've seen has been set up. Our steps are still 1 unit long and 1 unit apart. However, the behavior is a lot different, right? Not only is it going to end up looking like a downward sloping line, but the steps also went in like the other direction, right? Like the open endpoint here and the closed one here. And again, that's because now we're reflecting horizontally. So when we reflected it over the y-axis and we changed all the horizontal stuff, not only did the overall graph see a different direction, but the steps lined up in a different direction with the open endpoint here and the closed endpoint there. Okay? Is this all right with everybody for the reflective stuff? Okay? We're going to do the other stuff tomorrow, okay?